only keep 1,000 items on the client and basically throw away the ones we haven't used for a while. So it provides us a lights-out management of the cache on the client. Here you can see how a near scheme get works, and basically the first time you request some data, say data item B, you pull it across the client. So JVM1 here is requesting data item B. First time it requests it, it has to go across the network and pull it into its near cache or local cache on the client. The next time it wants it, it doesn't have to go across the network. It will be local, so it'll be a near instantaneous response. You can also access Coherence outside of a sort of gigabit network. So ideally, you want to put Coherence cache nodes on at least a gigabit Ethernet network segment, because it relies on being able to move data across the network very quickly. But often clients don't actually reside on that network segment. They may be on people's desktops with just a 100 megabit connection and TCP available. So what clients on desktops can do is they can connect over TCP and go via proxy. So on your cache node here, your application process 1, you've got a proxy service running, a bit like a database listener, and it allows clients who are outside of the network that Coherence is running on to actually connect in. So the client establishes a TCP connection to the proxy, and the proxy acts on its behalf, so it passes all the requests that the client wants to issue onto the rest of the cluster. And we call that Coherence Extend. It allows clients outside of the cluster to still issue .NET, Java, and C++ commands. So if you're a .NET or a C++ client, then that's how you will connect into the cluster. You'll connect via the Coherence Extend mechanism. You can also replicate clusters across a WAN. So some customers have caches or clusters located in London, and they want to have the same data available in New York. So in New York, they want traders, for instance, to be able to access information from a cache very quickly, but they want to see what's going on in London. So you can replicate information from one cluster to another. You typically wouldn't have a cluster spanning the WAN because of the high latency of the connection, but it's quite common to actually replicate information, and effectively the mechanism is where one cluster acts as if it's the client to another, and using this mechanism they can exchange information in both directions. So you can set up a replication mechanism using active-active, where both of them are changing the same data, active-passive, hub-spoke. There's all sorts of topologies you can create to actually share information across a WAN. As well as actually putting information just in a cache, using Coherence as a lookup table, you can also do a number of other things. And this is where we start to diverge from what's available in the sort of open source space in terms of caching. So one of the things you can do is you can actually query a cache just like you would a database. So you can say, for instance, give me every, well, in the query below, first of all, there are a whole range of what we call filters, which allow you to issue queries. And most of these are pre-written, and you can group them together or combine them to form pretty much whatever type of query you want. So here we're creating a filter to actually find out all the traders who have a particular trader ID, and we're also we're looking. There's a lookup table of trades, and we're looking up every trade where the trader ID is trader ID here, and have a status of open. And we're combining those two filters and passing them to Coherence. And Coherence will take that query, and it will run that query against all the JVMs in a cluster in parallel. And so that allows each JVM to search through its subset of data and return this response. And the client will pull that information together, so the client, from the program, so Coherence under the covers will pull all the results together and present it back to the client as a single result set. So it's very efficient because you're utilizing the whole all the processing power across your cluster to actually gather together the results. And you'll notice in the equals filter, the first equals filter, there's get trader in quotes. Effectively, Coherence is using reflection to actually query the value. So there's obviously an object in the trades cache, with an attribute, with a method called getTrader, and so it's using the getTrader string here to use reflection and issue that request against the values in the cache. And this diagram you can see now illustrates how Coherence performs that query in parallel across the whole cluster to maximize the processing power and to parallelize the whole operation. You can also do that with aggregations, so you can do things like sum, max, min. So you can say, for instance, give me the total value of all trades. You can use things like distinct as well. So there's a lot of similarities there with a database in terms of the type of queries and aggregation so you can execute. And you can also index attributes as well, and that means it's much faster to actually perform queries, just like you would with a database. The other thing you can do with Coherence, which again is slightly different to a lot of the open source offerings around caching, is you can Coherence can generate real-time events. This is similar to the Swing Java Swing mechanism. Effectively, a client can say, "I'm interested if this object changes," and you can pass a key, and Coherence will then tell you if that object which matches that key is updated, deleted. You can even get Coherence to generate events if an object because as well as actually specifying a key to identify objects you're interested in changes to, you can also specify a filter, which we've just described. So you can specify a set of objects that you're interested in changes to. And so if your set says every open trade, and someone creates a new trade and it's in the open state, you will get an event because someone's created something which falls into that set. So real-time events is a very powerful way of actually notifying clients or pushing changes to clients as data changes. Combining the capabilities of real-time events and queries, you can do something called a continuous query, and that's really a bit like a database materialized view. What you're effectively doing is you're issuing a query and getting a result set back, but that result set isn't static. So if any of the values in that result set you got back change, so for instance, if I say get me every trade that I'm responsible for, and the prices of those trades keep changing, I'll keep getting events streamed down to my client telling me that the volume of the trades have changed or whatever. So other useful and pretty typical use cases are things like gaming. So many of our customers are in the gaming sector. So if you're placing a bet and you stream a set of events down to your client, you do a query saying, "I'm interested in these events, these horse races or these football matches," and the odds change on those matches or those races, then the price changes will be streamed down to the client. So your view, the set of values which you're going to present on your screen will be constantly updating based upon what's happening in the cache. Coherence can also do transactions, again, which is something different from some of the open source offerings. You can do explicit transaction management. You can say, I want to lock an object based upon a key. I want to get the value, modify it, put it back, release the lock. Explicit transaction locking is possible in Coherence, but it's not very efficient. As I said earlier on, if you get and put data into a Coherence cache, the time is mainly spent on the network, so you want to reduce the number of network hops. Using explicit transaction management, you're looking at probably about 14 network hops to lock, update, and release the locks on an object. You can do implicit transaction management where you reduce the number of locks you use. So if you have an order and order items, you can say, okay, I'll lock the order and if I modify an order item, and I won't modify an order item unless I can get the lock on an order. So you have sort of a locking strategy. And as long as everybody obeys that strategy, you can make your locks quite coarse-grained. But it relies on everybody following the